In the rest of Chapter 4, we're going to cover 4 topics, all related to how neurons communicate. Okay? And the first thing we need to cover, and we'll cover in this video, is the resting membrane potential. So where do we start at rest? In the next video, we'll cover action potentials. So how do they actually do action? And then we'll talk about the synapse at the end of the neuron and connecting it to something else. And then we'll talk about neurotransmitters at the end. The resting membrane potential is critical to getting any action or any communication from your neurons at all. And we discovered this, well, Hodgkin and Huxley specifically discovered this by working with squid. And they worked with squid giant axons. Not giant squid, giant axons in regular squid. And it turns out that squid have this really long, large axon that you can pick up with a finger that run down the back of the squid from their little central nervous system, runs all the way along the back. And it controls this thing called a siphon that pumps water out the back. This is how squid move around in the water by essentially jet propulsion. They squirt water out the back and they move around. The axon that sends the signal to move them around through jet propulsion is large enough that Hodgkin and Huxley were able to study it with just regular sized electrodes. And what they found was that the axon was electrically charged, or at least had a potential charge in it relative to the fluid on the outside. So they plugged an electrode into the axon, they plugged a reference electrode outside of the axon, and they found that there was this electrical charge. So there's something going on electrochemically that is causing the axon to have this electrical charge, and they figured that there may be an electrical basis, a electrochemical basis for neural communication, and they started to study that in the squid. So what is going on in this resting membrane potential? So at rest we have this charge. Well, people started to look at the chemical composition inside the axon and outside the axon. And they found some interesting things, primarily surrounding the ions of sodium and potassium. There's a bunch of other stuff going on, but these are going to be the most important ones. So they found that outside of a neuron, there was more sodium than you would expect. And it wasn't balanced, so there was less sodium inside and more sodium outside. Conversely, they found, to a lesser extent, a bunch of potassium with the symbol K. K is a symbol for potassium. Na is your symbol for sodium. So there's a bunch of potassium inside the cell. A little bit less than there is sodium. And there's more potassium inside than outside. So there's this imbalance that's causing a bunch of positive sodiums on the outside, a little less potassiums on the inside, which is causing this imbalance where the inside is more negative, right? Because this is always just in comparison, right? This says more positive, this says less positive, so we get the negative charge. So we've got this strange sodium-potassium imbalance. And normally, what you would expect is if there's a bunch of sodium on the outside, it would just diffuse right on inside to balance out. That's kind of how chemistry works, right? But it can't. Under normal circumstances, there are these things called ion channels that control that diffusion in your neurons. And at rest, sodium can't get in. Okay, so sodium is blocked from getting in. It can go out though. Okay, so you got a bunch of sodium on the outside, and it can't get back inside. And this is just at rest. So your neuron is not doing anything. It's not being activated, but it is set up in this imbalanced way with a bunch of sodium on the outside, potassium inside. It turns out we have an active system for rest, which is we actively move sodium outside and pull potassium inside. We trade, and we trade in an unfair way. We trade three sodiums for 2 potassiums to create this imbalance. It takes energy to do this because it's an unfair trade chemically. And so there's this chemical called ATP. We need food to produce it. And so we use energy. We actively use energy to create this imbalance. Sodium on the outside, potassium on the inside. Positive, less positive, or negative. Okay? And this is what your neurons look like at rest. Weird, right? So why do we have this imbalance? Well, the consequence of this imbalance is that it creates something called diffusion pressure. So diffusion is when something moves, right? Diffuses from one location to another location, right? And there's a pressure for these ions to diffuse. Okay? The pressure occurs for 2 reasons. Number 1 is something called concentration gradient. In chemistry, you might know that molecules tend to diffuse from high to low concentration, if possible. So when something is in a high concentration area and it meets a low concentration area, it'll diffuse and then even out. That's kind of how chemistry works, right? And you know this if you've ever popped a balloon. There's a high concentration of air in a balloon and it diffuses out and explodes. Or if you've opened a soda can, there's pressure on the inside and it diffuses out. Or if you've dropped a drop of food coloring into water, you find that the concentrated color in the food coloring diffuses out and gets less concentrated in the water. So that's a concentration gradient. Okay? And we can think about our system that we have set up. Where is the concentration and where does it want to diffuse? The other aspect of diffusion pressure is coming from what's called electrostatic gradient, which is really just another name for the opposites attract principle. So positive charges are attracted to negative charges and vice versa, right? And you know this from examples like batteries. You got a positive and negative pole, right? And when you connect them together, they're attracted. That's how you get power, right? You know, table salt is NaCl, right? Table salt is a really simple chemical compound that's formed very easily because you've got a positive charge and a negative charge. They pull together, they create table salt. Okay? So we got concentration and opposites attract, electrostatic gradient. And we can think about how these apply particularly to sodium. It is going to be doing a lot of the action here. So where is sodium? Well, it's on the outside. Okay? So in our concentration gradient, if sodium is concentrated on the outside, where does it want to go? It wants to go to the inside. Okay? And if opposites attract and sodium is positively charged, then where's it going to want to go? Well, it's going to want to go inside because the inside of the neuron is negatively charged. Now, the only problem is sodium can't go inside, right? Because it's blocked. So there's a bunch of pressure. You got sodium, Na, 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 like Batman, right? So na, 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 na. It's concentrated on the outside, right? So it's concentrated here. It wants to go to the less concentrated inside. And it's positively charged, so it wants to go to the negatively charged inside. But sodium can't do that at rest. So the resting potential sets up pressure. It's like shaking up a pop can. Okay? And it's shaking up the pop can just ready to go. Cool? So this is the resting potential. Our neurons at rest are set up under pressure from concentration and from an electrostatic gradient so that sodium in particular is ready to diffuse inside. Your lecture slides have a video that breaks this down if you want to see another version of this.
We want to know how neurons communicate with one another.
Where the
So
sodium
we
is,
start
where
by
the
looking at how
potassium is.
communication occurs within one single neuron. One means by which signals can traverse the space of a single neuron is through local changes in a cell's membrane potential. To record a neuron's membrane potential, it is necessary to position the tip of one recording electrode inside the neuron and the tip of another recording electrode outside the neuron in the extracellular fluid. The difference in charge between the interior and exterior of a cell is called the membrane potential. When both electrode tips are in the extracellular fluid, the voltage difference between them is zero. When the tip of one of the electrodes, the intracellular electrode, is inserted into the neuron, a steady membrane potential of about -70 millivolts is recorded. This steady membrane potential of about -70 millivolts is called the neuron's resting membrane potential. In this resting state with the -70 millivolt charge built up across its membrane, this neuron is said to be polarized. The negative sign on the voltmeter indicates that there are more negative charges inside the neuron than outside the neuron. Let's take a closer look at what is causing this resting membrane potential. Like all salts in solution, the salts in neural tissue separate into positively and negatively charged particles called ions. There are many different kinds of ions in neurons, but this tutorial focuses on just two of them: sodium ions and potassium ions. In resting neurons, there are more sodium ions outside the cell than inside the cell, and more potassium ions inside the cell than outside the cell. Why is there this unequal distribution? There are 4 reasons. The first reason is because of the differential permeability of the cell membrane to potassium versus sodium ions. There are specialized pores called ion channels in neural membranes through which ions can pass. Each type of ion channel is specialized for the passage of particular ions, for example, sodium ions or potassium ions. At the resting membrane potential, the sodium ion channels are resistant to the passage of sodium ions. By contrast, the potassium ion channels offer little resistance to the passage of potassium. The second and third reasons for the resting membrane polarization have to do with the substantial pressure that exists for ions to enter or leave the cell. This pressure is of 2 types. The first type of pressure is electrostatic pressure. Electrostatic pressure results from the tendency for opposite charges to attract and like charges to repel. Because opposite charges attract, the -70 millivolt charge inside the cell attracts positively charged sodium and potassium ions. So, there is pressure for sodium ions and potassium ions to move into the cell. The second sort of pressure that exists is the pressure for sodium and potassium ions to move down their concentration gradients. Due to random motion, ions will tend to move from areas where they are highly concentrated to areas where they are low in concentration. Sort of like what happens if you place a drop of food coloring in a bathtub. So there is pressure for sodium ions to move into the cell, and for potassium ions to move out of the cell, down their concentration gradients. Despite these 2 sorts of pressure on the sodium ions, few of them enter the cell since, if you recall, the sodium ion channels are largely impermeable at the resting membrane potential. A few do manage to get through, however. The fourth and final reason for the resting membrane polarization explains what happens to those few sodium ions that do manage to enter the cell. They are removed by an ion transporter in the membrane, known as the sodium-potassium pump. The sodium-potassium pump consumes cellular energy to continually exchange 3 sodium ions inside the neuron for 2 potassium ions outside the neuron.
And this figure breaks down the thing that we were just talking about. So let's work through it just one more time, if it helps. So the first principle is the concentration gradient. Sodium is concentrated on the outside, potassium's concentrated on the inside. So there's a concentration gradient that's pulling sodium in and to a lesser extent pulling potassium out. Okay, so this is a concentration gradient. Because there's so much sodium out here, it wants to go inside, It will tend to diffuse inside. There's also a negative internal charge, right? We measured that in the squid. It's negative 70 millivolts inside. And so there's a electrostatic gradient to pull sodium in and also to pull potassium in, right? So we got all this pressure in from concentration and from electrostatic gradient. Meanwhile, we're fighting against that, right, by actively pumping sodium out and potassium in, okay, with this sodium-potassium pump. So this is the resting membrane potential. It's setting up pressure from concentration and from electrostatic gradient, and it's setting us up ready to pop, ready to go. In the next videos, we're going to talk about what happens when we open that can, and that's going to be the action potential, and then how things work at the end of the line when we get to the synapse and we communicate with neurotransmitters. All right, see you next time.